Hello again. So we ended.
Sir, one minute.
Yeah.
You can start.
Yeah. Hello again. The last lecture, lecture number 33, we ended with a question saying that how does one achieve distributed compliance, and for that how do we quantify distributed compliance so that we can incorporate it into topology optimization. There have been couple of methods, actually couple of methods, just two methods are essentially that are worth mentioning, and how those methods are able to achieve this distributed compliance is what we will discuss now. So, we will start with where we left off in the last lecture. How do we quantify distributed compliance? Okay. One way is to use this relative rotation. So, what do I mean? So, whenever these point flexures or edge flexures, something like this, edge flexures, the two elements, you can call them elements you have staggered like this. Actually, in finite element framework we will take these elements everywhere. So, these are all there, but for the purpose of design you keep this densities of those two the same and also those two the same, and as we just said in the last lecture, then instead of getting this point flexure, we get what we can call narrow edge flexure, slightly better than this, but not a whole lot. The other way, as we have already discussed in the last lecture, if you have hexagonal parameterization of your element and you divide this into 4 quadrilaterals for the purpose of finite element analysis, but otherwise it is basically normal finite element framework, but these two elements will have the same density, and let us say I will put indicate like that, or plus these two will have the same thing, this some other symbol or some other symbol. We basically have half the number of design variables if there are let us say n finite elements which are all trapezium like quadrilaterals, there are half of the regular hexagon, you have half of them to be the design variables and you get edge flexure. Okay. That is not what we want, but what we see in both cases, either edge flexure or point flexure, is that there will be a lot of rotation between adjacent elements. That will be the characteristic, that is how the hinges work, lot of rotation between adjacent, we can call them now cells, because these are called hex cells, right, or elements, finite elements that we have. So, whichever way you do, we will end up having lot of rotation, and that is what causes this is rotation, not rotation, lot of rotation between adjacent cells or elements. Okay. So, if you want distributed compliance, meaning if you want the entire structure of the compliant mechanism to undergo elastic deformation, we should not allow too much of this rotation between the adjacent cells or elements. So, we can look at a formulation which is somewhat complicated. So, what we do is, whenever a situation that is shown here happens, that is there is material here and there is no material in the diagonal elements, then what you say is you try to measure the rotation at that point. How do you do that? You define this vector A here and vector C here. So, this is there are two vectors that are shown. Between those two you compute the angle of rotation alpha or cosine of that, for because cosine is simply dot product. So, it is easy. So, A dot C. Similarly, if it is other way around, that is material is here and here and these two are empty, that is this is 1, 2, 3 and 4. If 1 and 3 are empty and 2 and 4 are full, then you can define the rotation cosine beta by take the dot product of this vector B here and then D there. Okay. If we do that, then we can pose an objective function such as what is shown here. Again we go for this MSE, which is flexibility or compliance, and this is more towards strength in a way, because we are trying to minimize the rotation, and hence hopefully the distortion energy did was minimize the strength, because distortion energy figures in determining the strength of the component, right. So, it is a flexibility and strength formulation is what we had discussed in the last lecture, but now we are looking at a formulation where this relative rotation is restrained, that is we do not allow between adjacent elements, we do not allow excessive rotation. So, the algorithm is trying to exploit by going for this one node hinges. Now, we close the door for the algorithm and then see what happens. How do we do that? Again, why do we need all of this? Actually, this is in this case phi rho is something like a filter, that is we put it only at the points where this type of situation occurs, that is two things are diagonally connecting. So, we have this filter functions there, okay, whether it is between 1 and 3 or 2 and 4. So, let me show this 1 and, so this is 1 and this is 3 and 2 and 4 you can already see very well. So, we put that between 1 and 3 we have this cosine alpha, between 2 and 4 we have cosine beta, we put that in the denominator and we sum over all the elements, so that we filter out or we pick out computationally all the possible things, even when these corresponding rows, that is indicator functions, whether they are 0 or 1. We try to do that over the entire thing, capture that, put in the denominator. That means that when we are minimizing negative, meaning maximizing, we are essentially make the denominator become as small as possible. That is, we are trying to minimize or restrain this relative rotation. If you do that, you are not allowing these hinges to form. That is what should happen. Let us see if that works or not. So, the problem now is one of restrained relative rotation. It is little complicated because we have to get this complicated function psi, which was there in the last slide, this psi. We want to make this psi as large as possible, because MSE and this both you want to make it large. So, we are minimizing negative of that, right. So, we have that psi with the negative of what we have. So, rows similar indicator functions, but we can also put our distortion energy constraint. This is the in a way a strength constraint, because distortion energy from which we calculate what we call von Mises stress. If you recall your discussions in failure analysis courses in mechanical design, we actually start, in order to derive the concept of von Mises stress, we start from distortion energy, where we take the total energy, subtract from it the isotropic component and leaving the deviatory component. So, that is basically a strength criterion. So, now we are moving towards a formulation for getting distortion for getting the distributed compliance. We have here already compliance, and now we have strength criterion as a constraint, and we have in the denominator of that this psi compliance, we want to maximize that, the negative minimize, and then here we have relative rotation, cumulative relative rotation of all the elements, the way we just discussed in the previous slide. I should add another word here calling cumulative relative rotation. Let us go back to the previous slide and see what we mean. See, this denominator here, this part is the cumulative relative rotation. So, we are trying to minimize that cumulative relative rotation or everywhere, so that everywhere it rotates only a little bit, bends a little bit. If you want a large displacement, which is we are asking, where we have this compliance requirement here, we want large displacement, but you do not want any two elements to rotate a lot. Okay, that is the idea of distributed compliance. That means that two elements having a joint or point flexure is not allowed. We want something to have the whole thing elastically deform, and we also put the strength criterion, so that in doing so any one point should not be stressed too much also, and then we have the volume constraint. So, this formulation actually works quite well, and its logic is quite strong, but implementation is a little bit difficult because of the complexity of this. So, we can actually compute, that is not a problem, but imagine taking sensitivities, that is for your gradients, then things become quite complicated, because you have cosine of angle, angle is the dot product of two vectors, and these vectors will have the nodal coordinates, and then we have these filters which have some exponential functions. There are other forms, but whatever you do, it becomes quite an ordeal. So, but in terms of logic, it does ensure distributed compliance. So, here let us look at an example. This one is the usual way, that is the usual MSE over SE formulation, and this is our new formulation, where psi we have negative of MSE divided by I can call it cumulative, that long summative expression, cumulative relative rotation in the entire image of the topology during the course of the optimization. You can see that we have joints, lots and lots of joints, right. Whereas here, are the joints not there? They are there actually. I am showing an example to show that somewhere else they have become more uniformly distributed, if you look at the top half, but other places it does have. But if we zoom in a little bit, adjust parameters, now you can see that at least it has become edge flexure rather than point flexure that happens here. Okay. So, by constraining or restraining relative rotation, we are able to go towards distributed compliance. Of course, there are some ill converged regions also. Here it is quite close to black and white, right, but here there are some things. Basically, the complexity of the formulation causes problems in implementation. Okay. So, that is the problem here. Let us look at another example. So, here again we see the joints here, the joints, right, and there is a joint, whereas here this has done quite well, because what we see here are just two beams that came from continuum formulation. So, if you look at this, we have a nice one beam there, another beam there, such as the one that one would sketch as just two beam elements. That is what we have. The symmetric problems, we have two beam elements. This came from this relative rotation formulation that we have, cumulative relative rotation, that when you restrict or restrain, then you get this. This is usual MSE over SE formulation. Okay. So, it is able to give us something useful. Now, let us validate it. So, in the sense that if you take the topology that we have, this is the usual one, this is the restrained relative rotation result. These two, let us actually clean it up, so to speak. These days MATLAB program software has routines where you can actually smooth it out by just using one of the ready made functions. So, let us smooth it out like this, where we have these flexures, these are all the flexures, and other one anyway is actually both original one, that is this one, the deformed one are shown in this figure. And why are we not seeing deformed one here in the discrete case? By the same force, it turns out that it is actually quite stiff. and this is flexible. That is actually validation. What you see here, this is this curve, here we have output displacement, everything is the same. The two simple example use a similar data, and we got two designs using the usual MSE over SE, and with and without this relative rotation thing, input force here. So, you see this one, this curve, small displacement, it is linear, this shows a little bit of non-linear, but anyway that is not the point here. You get a lot more displacement for this mechanism as opposed to this. Okay. To prove to you, I even have prototypes that are made using this, and this is true for the other example where there was actually hinges occurred in the distributed thing also. That is why this is the restrained relative rotation, or I should always put restrained relative rotation formulation, and this is our usual MSU over SE. Again this is the output displacement, this is input force. Here it is only slightly better because this also has the hinge, as we already saw. The example 1 that we showed, this also had a bad hinge. Okay. We could not completely avoid it, maybe the tuning of the parameter was required in the example, but we can see both extremes, right. So, in this particular case that this is very stiff, we can see by looking at a prototype that I have. So, here if I look at this, this is our discrete, both were given by topology optimization. This is discrete compliance and this is distributed compliance, distributed compliance. We can, when you look at them, you see this where the joints are, right. These are the joints, and of course symmetric. So, we have joints here, 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 right, whereas here it is smooth beam like this. These were the same almost amount of material in the topology images, and we have made these for the purpose of making prototypes. Which is better? Clearly, as we will see, the right side one we have this. So, when I apply force, this is the input force here, it is supposed to go and pinch something. So, that is the output here, so it pinches. In fact, this has a quite good mechanical advantage too. When you put your finger in a mechanism like this and apply force, you actually feel a lot of force, and it is quite flexible. Now, it looks like I cannot say one point is experiencing a lot of elastic deformation compared to other points. More or less everything is deforming. Of course, these handles are intentionally made so that we can put our finger over here and do that, otherwise they are not really important. But otherwise the rest of the structure, at least I would say 80-90% of the structure is actually deforming, as opposed to, let us take the prototype of the other mechanism, which is what we have to orient you. Yeah, I should put it like this, right. So, or upside down, right. So, this is how it is. So, by the right hand one, so when I apply force, it is going, right. It also seems to be flexible, but it is actually a lot more force is required to actually apply this. And moreover, if I put here my finger and try to feel the force, it actually does not give as much force. And in fact, if I am not careful here, what it will do is actually go out of plane, because its flexibility in the out of plane direction is more than in plane, it would actually go. Okay. So, and of course, if we closely look at it, these are the ones that are going to undergo plastic deformation very quickly, and they might even fail there. So, the MSE over SC formulation, when it gives hinges, it is very good for designing rigid body linkages rather than compliant mechanism. Compliant mechanism, if you want distributed compliance, we have to go for this relative rotation restraint, but it is a little involved. So, we look at compliant mechanism topologies as something that gives us conceptual design for us to sketch and try to avoid the hinge based designs whenever it is possible. This is what people have done, and there is an alternative way instead of this complicated way of computing vectors and the dot products and getting the relative rotation quantified. But if you think about our usual strain, shear strain. So, shear strain, if I say epsilon x y in 2D, that will be dou u by dou y plus dou v by dou x with a half, where u is the displacement of a point in the x direction. That is, if I take a elastic body, let us say I have x and y axis, I have an elastic body. If I take a point, the displacement of that is u function everywhere. So, u is actually a function of x y everywhere, and likewise how much it moves in the y direction, v, I can call it also a function of x y in 2D. Then if I take an element there, if I take an element around that differential element, then the shear strain in it epsilon x y is given by half dou u by dou y plus dou v by dou x, and that is actually nothing but, when I say shear, if I take an element, the shear is how it would actually go like this, that is what we call the shear. So, this angle we talk about shear strain. So, if you take this for every element and basically integrate it over the entire domain, because this is the a measure of relative rotation in a way, how much the element is distorting. You can take this, how much shear is there with this element and the next one, you take the difference and quantify rather than going for the vectors. This can also be done, and it gives similar results, meaning that it does avoid hinges, not always, but with tuning you can make it work, but it is still quite a way difficult formulation to implement, but that is there, and there is no other idea that directly tackles this problem. People have tried a lot of methods to avoid this one node hinges, but this relative rotation, containing the relative rotation, restraining it seems to be the best way. Recently about 5 years ago in 2011, I think the authors are Wang and Lazarov and Sigmund. Their paper appeared in Structural Materials Optimization volume 44 in 2011, page numbers are given here. So, what they did was a slightly different way. They used what they call erosion and dilation method. What they do is, let us say in the course of topology optimization, you have all the indicator functions rows everywhere. What you do is, every element that you have, you erode it a little bit, meaning that you make it thinner. That is, if I have, let us say an element like this and an element like this, right. So, you make this element a little bit smaller, rather the width or whatever. You can see compared to this, this is a little bit weakened, as if it has not eaten for some time, right. It is eroded, whereas this actually has become fatter, it is fed more. So, they use this erosion dilation, which is a concept again in image processing, where you can take an image and like changing the contrast of the image, you can make things go narrow or fatter. So, they use that, and for any given intermediate design, they construct a model that is eroded and they construct a model that is dilated, expanded, and in both cases, in all three cases, I did not say both cases, all three cases we compute your performance measure, whatever it is, MSE, SCR, or 5 different things what we talked about, any that you want, you compute your performance measure, take the worst one and try to improve it in the optimization. Optimization always, you start initial guess, your performance measure, you try to improve it. Here they take the candidate one and try to erode it and dilate it, and all three you compare, take the worst one and try to improve upon it. That way you get a design that kind of looks distributed. You can see here, so these are distributed but very weak, these are like almost like point flexures, right, whereas here is little fatter, right, and of course this is the fattest design. So they try to see in a given application, you try to get something that is intermediate between. So this is the intermediate one between eroded and dilated, so that that particular one, if it is eroded, it will become very weak, or your performance criterion something a stress constraint or whatever is compromised, it will not go towards eroded design, it will not go dilated design, that will make it very stiff, you do not get maximum output displacement, they do this. So these also in implementation wise not very straightforward. It can be done like all papers in the published papers, you have a method that is tried out and tested and validated, but for us to, for everybody else to use, it is a lot of work. But that is how the state of the art is in terms of this distributed compliant mechanisms. And again to conclude, all that we have taken today is taken from this paper that talk about design of distributed compliant mechanisms in this journal. But what we need to understand is that avoiding excessive relative rotation is the key to distributed compliant mechanisms. We should not let things bend too much. So let us look at actually what exactly constitutes a excellent distributed compliant mechanism. So let us look at that point before we end this lecture. So what exactly would be an ideal distributed compliant mechanism? So ideal distributed compliant mechanism is one which has uniform relative rotation, uniform relative rotation, that is the bending, I am calling rotation to mean bending or twisting. A compliant mechanism in 2D works by bending, in 3D if we have beams there will be bending and twisting. Okay. I am not so worried about stretching, because stretching like tension, it is actually okay. In fact, compliant mechanisms that are based on strings in tension are quite welcome, because they will be quite strong and they will be nice to deal with. We are worried about bending. So bending or twisting is focused onto a few regions, what we call discrete regions, that is actually bad, because that is where things will break, we want to avoid that. So we want to have uniform relative rotation. Since this is not enough or difficult to implement with any formulation, although it has been done in two papers that I described today, we also want to have uniform strain. At the same time, it would mean that we will have uniform stress also. This is one characteristic, this other characteristic, uniform strain or stress. If we have that, that is actually very good, but compliant mechanism unlike structures cannot live with only uniform stress, because it has to have functionality. So there is disparity in terms of some regions being more stressed compared to other regions. So the first one is uniform relative rotation, second is as much as possible we should have uniform strain and stress throughout compliant mechanism. But there is actually third one to characterize this distributed compliant mechanisms, which is uniform geometry actually. But what do I mean by that? Most of the compliant mechanisms are slender beam segments, that is what they have in them, and those slender beam segments should be uniform in their size profile. That is, you want to have things that are like this, not like this. So this actually amounts to again the hinges we are trying to avoid. We want things that are uniform, wherever you take you want to have uniform geometry, so that bending and twisting will be more uniform. You need to have uniform relative rotation, that is our aim, and ideally aim would be uniform stress and strain, but those things can be achieved if you have actually uniform geometry. Is there such a design? The best thing that comes to my mind or comes to anybody's mind is actually our helical compression spring. Think of helical compression spring or extension spring, helical spring. The geometry is uniform, the cross section, I am talking about the spring that is there in all ballpoint pens and so forth, right. So, we have let us say circular cross section, the same circular cross section is there everywhere. So, that has uniform geometry. And does it have uniform stress or strain? In fact, that is true. Wherever you cut, as you would know from analysis of the beam spring, the same torsion is there at every joint, because the force times the radius. If the helix is normal rectangular helix, we have the same torsion torque everywhere. So, you have same strain and stress. Okay. Of course, not at the cross section, maybe the cross section as a whole. With the cross section, if you make it a helical compression spring with annular cross section, everywhere also it will have the same stress and strain. What about relative rotation? In fact, that is also true, because in the case of a helical compression spring or extension spring, when we are compressing or extending, what is happening is everything is actually twisting a little bit, the same amount, because every section has the same torque, everything is rotating a little bit, and no wonder we see this helical compression spring everywhere, not only in engineered components, but also in proteins and everywhere, and creepers everywhere. This is one of the best designs that one can have when it comes to elastic or compliant design, because they have uniform geometry, uniform stress and strain, and uniform relative rotation. Everything is contributing towards the final goal of what we want. Okay. That will be the ideal distributed compliant mechanism, and this is where, to achieve what we have listed here, a lot more work is needed, and that is an open problem in compliant mechanism synthesis. So, the last lecture and this lecture tell us why these one node hinges occur, and it is actually a problem in any of the formulation that we have discussed, 5 different formulations. So, we have discussed 2 different formulations, one in detail, the other one by Wang, Lazarov and Sigmund. We just gave a reference, you can look that up, how they used image processing, erosion and dilation concepts to get something that is distributed compliant. But the idea is that we need to have relative rotation restrained. If we do that, we do get distributed compliant mechanisms. Thank you.